And this paper is much better than previous paper, and it's a continuation of that. It's built on top of the previous lecture, and they use arborescence-based supervised clustering. I have a lecture on Deep Learning 2032 that I explain supervised hierarchical clustering. Lecture 21, I guess. So they draw inspiration from that article, same authors, I guess. And so these are positive examples that are related to this. I explained this article in lecture 21 of Deep Learning in 2032 playlist. So the idea is that we present novel training and inference procedures that fully utilize mention-to-mention affinities by building minimum arborescences. Those are directed spanning trees over mentions and entities across documents in order to make linking decisions. We also show that this method gracefully extends to entity discovery, which is really important. Do not confuse entity discovery and those things in zero-shot learning are for different purposes. So distinguish between them. And enabling the clustering of mentions that do not have an associated data in the knowledge base. And then they evaluated it on the zero-shot learning and mentions dataset, which are the greatest datasets for biomedical checks. So we want to recognize these entities, to link these. For example, this is a mention. We want to link it to this entity in our knowledge base. Some of them are new entities, such as this one. We don't have this one inside this knowledge base, so we discovered that. So entity linking is particularly challenging in zero-shot setting, where not every entity is labeled training data. In such settings, we rely on entity descriptions, types, analysis to form entity representations, which are used for linking predictions. So the problem formulation is that we have entity linking problem, we have zero-shot linking problem, but here it is important to note that the distinctions between zero-shot learning, as I said, and the discovery. In the zero-shot learning, entities are really known in the knowledge base ahead of time, but there is no training data. That's why we use description. But in the discovery setting, we do not know at all. We do not know all of entities a priori, and our performance then is evaluated in terms of correctness of clustering, which is a bit of ambiguous things. All of the clustering things is ambiguous because it depends on your measure. There are four main components to our approach. They use graph-based dissimilarity measure models to provide edge weights, approach for inferring latent graph, and finally building the constraint clusters. And for graph-based similarity, they use this dissimilarity function between two nodes U and V. And for edge weights, they need to learn this function phi, which is parameterized, of course, and also this function psi. So between mi mention and another mention, we have this w, mi, mj. From mention I to entity e, we have this weight we and mi. And we use these encoders. We have two separate transformer encoders. Of course, this is just one paradigm. You can combine it. But here in this article, they use separate things. And each has pros and cons. So the affinity models are simply the inner products of associated and encoded representation. Just dot product of this vector and this vector, transpose of this vector, and then so the same thing, dot product of encoding of entity and encoding of your mention. And just like in previous lecture, we have left context, right context for each mention. And for we also have a title and description. So all of these are standard, like previous lecture. What is interesting is that this approach has several drawbacks. The directionality of the nearest neighbor is ignored, leading to added noise. And the resultant graph edges that clearly cross cluster boundaries due to this approach, forcing all pairs of mentions to be connected. So it's really too complete. This graph is too complete. We need to remove several of these edges. And so we form clusters and make predictions. So there are three constraints that we should satisfy. First of all, each cluster should have just one edge, one entity, and also the distance, the similarity should be less than a threshold. Lambda is a hyperparameter just. And so this is an example that you link each mention to some entities and you're clustering these things. Because in each cluster, so what is our constraint? One of them, as I said, in each cluster, you have only one entities, but several mentions. In another cluster, you have several mentions, but just one entity. And you connect them together. So this is kind of clustering. And we use clustering spanning arborescence. So the training, so if you've seen my lecture, I've explained that article for hierarchical supervised clustering. So we want to appreciate this, and we do not encourage this one if it is between something, because this indicator function says that if it is inside the training data, we appreciate it, but if it is not in our gold relations, then we do not encourage that. But the last function requires simultaneously increasing the likelihood of positive edges and decreasing the likelihood of negative edges. And so we always use these data sets: med mention, zero shot, entity linking, entity discovery.